Good day, everyone. In this lesson, we're about to cover how to do upscaling in YOLOIL. That means petrophysical summaries and upscaling for several purposes. That is to summarize one petrophysical property for a sum. This is the web page of YOLOIL that explains how to do that. So we're going to take one particular well, actually two wells, and see how can we do some of this stuff. Okay, let's start. So here to the right window, we have the results of already processed well. And to the left, we are going to follow the steps, the properly steps to reproduce the results. Let's start doing that. So here we have 1, 2, 3 sums. Pull sum A, prime sum B, and pull sum C. So we have 3 sums. Well, let's call those some units. So here we have this bar is what we call sums. The middle yellow bar is that we call phases. Those are the related to the minerals, the environment, whatever. These are Aeolian sands. And here we have flow units. So we have a prime phase sum and 2 pore sums. Here we have a shadow on that prime phase sum. Let's do that on the other well. So you go here, stratigraphy, prime pay, you put a shadow, a shade. And now you have this shaded. Okay, let's start right away with the cutoff system. We have here the porosity space. We have put a filling to the right of the threshold. So if you click here with the center mouse button, you see a cutoff of 15%. So we are highlighting the porosity that exceeds 15% or more. And regarding water saturation, you put more or less here. We have here around, well, 61% more or less. Cutoff of 61%. So that is the cutoff system we're using for porosity and water saturation. Where you see your fillings. So basically you see here effective porosity 15%. To the right of 15% we'll have this shadow value. And to the left of 0 we may put transparent white. We have nothing. Okay, let's do that with the other one. This one. Okay, let's put this one in white transparent. Okay, good. Likewise, we do the same with water saturation. Choose a threshold, 61%, and to the physical right, not to the number, to the physical right of 61, that means 61 and less water saturation. The scale 0.8 to 0.2 is a reverse scale. We have the shadow. Water saturation, put this one. Perfect. So these are the fillings. Let's start computing the first upscaling. So let's start with net sand flag. So we want to build a curve that says when we pass the cutoff for porosity to consider that the rock is a net sand. The rock is a sand. So we have a porosity cutoff. -1 will mean that the rock doesn't pass the cutoff. In this particular case, the porosity is 15% or less. The value +1 means that the rock passes the 15% cutoff or more. +1, it means yes. And 0 means I do not know. That happens in some cases where you have the value of porosity -999.25 and case similar to that. Okay, let's open that. Here, the first type of upscaling, curves and cutoff, you have to specify your porosity. Let's have a look. You hover the mouse here on the question mark. Your porosity is the curve number 15. There is an asterisk there, and those asterisks means that the curve is already plotted into the display panel. And now you have to specify the cutoffs of the thresholds. The threshold, the cutoff for porosity is 15% and beyond. Beyond means typically up to 40%. let's go to the zonation tab. We have to process, we want to process the whole column, and we want to detect the indicator flag curve. So let's choose a mnemonic, SAN flag, a Unisar flag, that is -1, 0, or 1, depends upon the detection, and use a description. -1 means no, 0 means unknown, and +1, it means, well, I passed the Catus perfectly. You run that and see the display. So it created a curve. Let's see the display. Okay, so we need to put here in this track, NetSAN flag, put that curve. So where is that curve? Let's see, is this one, pay flag, the curve 22. Display steps tracks, porosity, SAN flag 21. Okay, let's put is -1 to 1. Let's put 1.5. After you put the SAN flag, the mnemonic, the unit flag, and the description, you run that, you compute, and it creates a curve. We'll create this curve, which is SAN flag. Let's see where's that flag, that curve. It is this one. It's the curve number 21. So you go to display. Here in the track number 4, which is NetSAN flag, you plot the curve 21. This one, okay. Remember that the curves are from -1 to 1, so I will plot from -1.5 to +1.5 to don't touch the walls. I want straight line stroke, and the thickness may be thin. This is the one, this is the flag. So you see it matches where you have, it passes the cutoff from porosity and the flag. So here, for instance, we have, it passes the cutoff, so we have here the SAN flag 1, and we have their porosity 17%, is larger than 15%, so that means the green filling. In regions like this, we have porosity is 11%, 11.7% or something. So it's smaller, it's less than 15%. So the SAN flag is -1. So here it means I know that it didn't pass the cutoffs. This is a different case. In this particular example, where the porosity is unknown, the porosity -999.25 is unknown. So I cannot classify that as a NetSAN, or we cannot classify that as a no. So that means I do not know. So the Trillian logic says you 0. 0 means I do not know. +1 means I know. It is a rock that passes the cutoff, and -1, it is a rock that didn't pass the cutoff 15%. Okay, you do the same for the next upscaling. Let's go to the next upscaling. Let's go to the net pay flag. We need to have the values -1 and 0 and +1. -1 is no, 0 means I do not know, there is uncertainty, +1, it passes the cutoff system. For net pay, you have to pass 2 cutoffs. In some cases, you can put more than 2, like shade threshold, permitted values, and so forth. This is a clean SAN reservoir. If we use a system with porosity and water saturation, is usually enough. So let's see how to do that. You open here your cutoff system, you specify to one for porosity. Porosity, yeah, you hover here, is the curve number 15. Yes means from 15% and beyond, up to 40%. And also water saturation. Water saturation, you hover the mouse here, is the curve 16. You need to have a water saturation of 61% or less. You don't want too much water. In this particular example, the cutoff is 61%. That means 61% or less. You put the system. Zonation is the same. You put a curve, the mnemonic name, pay flag, the Unisar flag, and the description. -1 means it does not pass the cutoff system. It has to pass both. It has to satisfy the porosity cutoff system and also the water saturation cutoff. It has to pass two variables cutoff system. It has to pass both. If you fail at this one, it will be classified as -1. If you pass both, porosity is larger than 15% and water saturation less than 61%, it will be a yes. It will be a pay zone. If you have some problem with some curve -999.25, your will say, I do not know, using the Trilogian system of logic. Let's plot that, compute that. It creates a curve, which is pay flag is the number 22. Let's plot this one, 22. You go to display, you go to the net pay flag, it was 22. You hover the mouse here, you have more help. This one, display it, -1.5 to +1.5 to avoid touching exactly the walls at -1 to +1. Straight lines and thing. Let's plot that. This is the pay flag. Net is the summation, and pay flag is the flag at that particular depth. Here is 0, means I do not know because we don't have porosity. We do not know how to classify that. Perhaps it's pay, perhaps it's not, whatever. Simply we don't know. So this means 0. Let's go deeper. This is interesting. Here we have some cases where we have net sand, like this one. We have a porosity of 15.8%. But what happened with the water saturation? It passes the porosity flag, but it didn't pass the water saturation cutoff. So that means it has to pass both. So it's classified the pay flag as a -1. It didn't pass both. So it is not a pay rock. And this is the prime pay. Let's go beyond that. Effective porosity upscaling. We need the effective porosity in a particular zone. Not a continuous course, in a summary value. We need an equivalent value for a particular zone. So let's open this one. There are several types of upscaling. There are many. In the case of porosity, your upscaling is an intensive upscaling. It is different from extensive, which is like net pay or something. It is some sort of averages. Intensive upscaling, course and cutoff. So we have to declare what is the physical property curve you want to process. You want effective porosity. You have to specify the curve. The curve is the number 15, you see there. You have to specify the cutoff for porosity. If 50% and beyond, and the curve number 15, to define pay, we need saturation, both. Low water saturation is 16. So curve 16, your water saturation has to be 61% or less. You go to zonation. I want to compute effective porosity, but where? I want to compute that for units. For this pool zone A, B, and C. I want 4 units. You put here, you have many choices. Or column formation members. Hit here unit, flow units. And you may specify what are the flow units you want to process. We choose this one. You know, these are the ones, because if you go to display, you go to stratigraphy, you see here A, B, and C. These are the UID are for A, B, and C at 589, 190, and 462. If you want to process only those are the unique ID for those units. You click that. You run, and you have your results. You have the upscale porosity after cutoffs. That means for pay, all of them are beyond 15 because that was the cutoffs. It's 15 and beyond of that. You have one value for zone A, another value for zone B, another value for zone C. You see the completeness here. That is the percentage of how complete is your computation. In this case, it is not 100%. Why? Because we have a region with it is completely undefined. We have -99.25. So for pore zone 8, it didn't yield 100% of the completeness of the information. Just that number. For the other zone, we have all the cores or the values. It yielded 100% of completeness. That's this column. Let's make a plot on that. So we define a curve which is upscaling porosity, volume divided by volume, upscale porosity in units. So let's see here what the curve produced is the curve number 23. Let's plot that. Let's put here in the pore space track. Pore space 23. 23, this one. Let's put in black, straight and thickest as a reference. This blank straight line is the upscale porosity. It's a constant per zone. You want one value upscale per zone A, another value per the zone B, and so forth for the zone C. So we have for the zone A, we have the upscale porosity 15.83%. For the zone B, prime P, we have the upscale value is 16.7%. And you see the porosity effective is a curve, but the upscale value is a constant. We want a constant per zone. Let's do that the same for water saturation. For water saturation, the upscale water saturation in prime P. You open that, it's still intensive, some sort of average thing on that, and the constant cutoff, okay, you have to specify your properties water saturation, and the upscaling of water saturation depends both on porosity and both on water saturation. The correct upscaling of water saturation, it is not to average water saturation, it needs porosity in the equation. It's the multiplication porosity times water saturation gives the water volume, then you have to divide it by the whole pore space, so it uses both. You have to specify that, your curves, water saturation is 16, and porosity 15, 16, 15, 16, and put the former cutoffs. And the zonation, you hit here, you put the interested zones you want to process, in particular this case, you put a curve, you want to create a curve of the upscaled curve value. Let's call upscale water saturation, and that's it. Let's run that, and you have your upscaling as a table. The same problem with the completeness of the zone A, which is not complete. And we have water saturation 38%, 48.5%, and close to 60%. Now you want to plot the upscale water saturation. You go to display. We need to put that into the water saturation track. And what is the curve? The curve is the last one, is the number 24. So you go water saturation, the 24, that one. The 3, this is the one. I selected black, and I selected the same scale as the water saturation, 0.8 to 0.2 to have more sum of the value. Put the straight stroke and thickest, and let's see how it looks. Okay, this is the black, this is the one. So we have here a upscale water saturation of 38%. You see how the continuous water saturation is different. It moves, it's a continuous curve. And we have a staircase pattern here. So the water saturation increases, look at the scale. Increases, moves to the left, higher water saturation. And here we have 0.59. That's it. There's another upscaling which is very interesting. Let's go again to the scale. Net sand in units. We already had computed net rocks. Now we need net sand inside unit. We need the summation of net sand pay flux inside units. So you type this, you open this. Let's see how we did this. You select extensive upscaling and cross and cutoff. For net sand, you need only porosity, and you specify your cutoff system to have the porosity larger than 15% and less than 40%, and the zonation, these zones, and that's it. You run that, And they are. These are your net sand in feet for zone A, B, and C. The prime pay, of course, is better, 28.9. So that means that 28.9, it is essentially the summation from here to here in TBD 10.7 delta TBD plus this one, and so forth, the other ones and this one. Of course, remember you have to create your well path. This well is not vertical. It has some important inclination. It ends in 15 degrees against the vertical. You have to correct the inclination of the well. You do the same you want for net pay. You want to compute your net pay in unit. What is your net pay in each unit? Do the same. It is an extensive upscaling, the number 3, extensive. The curves are cut off. Now you have to add not only porosity, but you have to add water saturation. You have to add water saturation, both cutoff system. And go to the zonation tab, and you specify units, and what are the units you want to process. You run that, and these are your results. The best zone, the zone with more net pay is the zone prime B, prime pay, or called B. And what happens if you unselect this one? If you unselect this one, it will process everything. Not only this unit, but all of them you compute. It will give you the computation of many other zones. Let's go to the other upscaling. Net to gross. Net to gross, when you say net to gross, we have to specify what is the net. There are many types. For instance, we can compute net sand to gross, or we can compute net pay to gross. Those are very important. Those are very standard. The difference is that this one is just only porosity, and this one uses porosity and water saturation. Or if you are working with some clay reservoirs, you would like to have a cutoff system that uses typically the standards one cutoff for B shell, usually 30% or less, or 35% or less, a porosity cutoff, and water saturation cutoff. So let's go to these ones, to this net to gross, net sand to gross. Let's see how it looks. Open that, so you hit here the number 5 type of upscaling, net to gross, and where are the curves? So you have to specify the cutoffs for porosity. That is 50% or more, and check and filter, yes, filter by that. Zonation, again, I want to process the flow units, these flow units, for all of them. You put here, you compute all of them. But in this particular case, we're only interested in these ones. These are the ones. The one that has the higher net to gross, net sand to gross, is the prime B, 75%. The prime pay usually have the best of everything. The next one is the net pay to gross. As long as you declare the deviation survey file, it has the proper correction. Geology automatically applies the correction to verticalize your computations. As long as you put that you are okay. Net to gross, the curves, you have to specify both porosity and water saturation, because this is net pay to gross. So you have specified the curves, 15 and 16 for effective porosity and water saturation, and the cutoffs, that means 15% and beyond, and 61% water or less than that. And zonation are interested in flow units, and these flow units. You compute that, and here you are. Again, the prime zone has the best net pay to gross value, 71%, which is very good. Other upscaling, this one is interesting, is the hydrocarbon column in net pay. That is simply volumetrics. Hydrocarbon column in net pay, this H-pole, that's the name we want to talk about. In some textbooks, some people call about porosity column, which is, I think it's not the happiest name for that, nomenclature for that, because it has to involve the porosity, and it has to involve the water saturation. So you would prefer to call that hydrocarbon column, or oil column, or gas column, whatever. That is the multiplication of porosity times hydrocarbon saturation, which is 1 minus water saturation times the height or net. That means once you take that multiplication, it yields you the hydrocarbon column in pure hydrocarbon, pure oil. That is, if you pour oil in a beaker or something like that, in a recipient, on a glass, that is the height of pure oil. That means you multiply that by the area, you have your volumetrics. You have the hydrocarbon column in foot. You multiply by the area, you have volumetrics of oil in feet by acre. Just simply take your value close to the well and see what is the area surrounding that. You multiply that value by the area, and that's the volumetrics in that sum. So let's open that. So you choose here the number 4, total hydrocarbon column. It knows how to do that. You have to specify phi, water saturation, and H. Put curves. You apply the cutoffs. You want the pay cutoff system. You need to specify porosity cutoffs and water saturation. If you are on a clastic environment, you need to specify B shell. Not in this particular here, with clean equivalent sands, for instance. That's it. You go to sonation. You put units. It will compute your FISO H, or SOFI H, as some people say. That's it. That is the upscaling output. You multiply those values by the area, that is your volumetrics. That's it, very simple. Let's do some exercise with permeability. Minimize this and open this one. This is a very nice example. Here we have in pore space, this track, we have the upscaling of these members. So here we have the very leftmost bar here. They are formations. We have a formation B. This is an aeolian sand with some dolomitic spikes. Inside the formation B, we are defining members nested in the formation. So we're calling that zone 1, zone 2, zone 3, zone 4, and zone 5. You go to, let's review quickly the upscaling for porosity. You go to, upscaling of porosity, upscale phi, upscale over equivalent effective porosity in members, intensive upscaling. In this case, we are not applying any cutoff system. That means we are applying the gross porosity. We need representative of the column, maybe for a simulation project. So you need to take into account zero porosity. You have to model shells or whatever. So you need the correct pore volume there, not the pore volume that exceeds a cutoff system or something. That is different in this particular example. In sonation, you specify members. And the upscaling curves, I want the equivalent porosity or upscale porosity members. You run that. These are the ones. You display that. We don't have anything here because we don't have members. The members start here for formation B. So these are the values. So this is an equivalent porosity for that member Z1. It jumps to a different one, it's a little bit slightly higher, and so forth. We have a pore member here, the Z5. Let's do the same thing for permeability. In permeability, for zones, for packages, we have two types. We have horizontal permeability, which is the default, and also vertical permeability. Let's see that. Let's see how to do that. You go to upscaling and filtering, upscaling horizontal permeability in members. Intensive. That is interesting. You go to horizontal permeability, your flow, vertical well, your flow is essentially horizontal. In this particular upscaling, the correct upscaling of horizontal permeability, it matches the same as the conventional arithmetic permeability average. Not in vertical, but that happens in horizontal. Curves and cutoffs, you specify horizontal permeability your curve. That is the 46, this one. No cutoff here. This is a simulation project, so we do not want to cut anything. And zonation, go to members, filter by members, and you write the mnemonic for the output curve, compute, and that's it. These are the results for C1 up to Z5, your horizontal permeabilities. The data is complete, 100%. Let's go to the display. And the display is the one. The red one, the upscale K horizontal, this one. So it's slightly different than the continuous curve because it is a logarithmic scale. In some cases, it's not very easy intuitively to follow that. That's the correct upscaling horizontal permeability. This is a poor sum. And let's go now to the vertical permeability. The vertical permeability is a little bit tricky. Let me go toggle off this one. Permeability. Let me toggle off this one. Something like that. This is the upscaling of horizontal permeability. What is regarding the vertical permeability? Here we have a permeability. You see K horizontal 4.3 or around 1.9. Here we have a very low permeability. That means the vertical flow from here to there is almost nil. It's very, very low. So the upscaling of vertical permeability should be quite different. In spite that the horizontal is okay, we don't have almost any vertical flow here. And also here, so the upscaling of vertical permeability is very sensitive to seals and buffers. And also here. So let's go that, let's see the upscaling. Go here. Okay, now your upscaling choice is vertical permeability upscaling. We have two parameters. So basically what Yoloil does inside is to use a power average. And you specify the power parameter and the core scale KB to KH. This is this. You have your values of permeability are essential horizontal permeability even after calibrated with core. Essentially you have horizontals. Then you have at core scale you have a ratio, perhaps it's around 0.5. So Yoloil needs to do that, and then Yoloil internally makes a pile, a vertical pile of pieces of core inside the log and compute that. That is quite different. Then the curves and cutoffs, you specify here the permeability, in this case the horizontal, which is 46. Then as Yoloil knows 0.5, it converts an approximation to the horizontal to vertical, and then use this for upscaling. That is the power averaging, general power averaging. No cutoffs. Then the zonation, you select members and your curve. You run that, and these are the results. They are quite low permeabilities. Let's go to the display and go to permeability and see that. That is the curve 59. 59 here. Okay, let's choose a green color, something like that. Straight and thickest, and see how it looks. They're on the same scale. It is quite different. You see this value of the horizontal upscaling is 16 millidarcies, but the vertical is 0.016 millidarcies, quite low, because that computation is heavily influenced by this buffer here. The same here, it's a little bit better. We don't have so thick buffer or seal like this one, but we have some minor buffers, but it penalizes a lot. We have here something like the horizontal upscaling is 35.4 millidarcies and the vertical is 0.03 millidarcies. So it penalizes, as long as it see a baffle or a seal, it penalizes that. Here, the penalizing is a little bit much less. We don't have very low values here, and here, and here. Thanks for following us. Be patient to see this video. Thank you very much. Have a very nice day, the rest of the day. Goodbye.